This is the last video in the series on section 4.9. In this video, I'll talk about motion problems. So earlier in the semester, we talked about the relationship between position, velocity, and acceleration. And what we said was that velocity is the derivative of position, and acceleration is the derivative of velocity. So if we take those relationships and reword them using antiderivatives instead of derivatives, we get something like this. Position is an antiderivative of velocity. Rather than saying velocity is the derivative of position, we say that position is an antiderivative of velocity. Remember that antiderivatives just switch around the relationship. So instead of saying that acceleration is the derivative of velocity, we'll say that velocity is a derivative of acceleration. So in this way, if we know something about the velocity, we can figure out the position. If we know something about the acceleration, we can figure out the velocity and then figure out the position. So those are the kinds of problems we're going to be working on in this part of this section. So here's an example. Anna and Bruce are running in a race. Anna begins at the point s of 0 equals 0 and runs with velocity v of t equals 2t. Bruce begins with a head start at the point capital S of 0 equals 8 and runs with velocity capital V of t equals 2. The capitals there are just to distinguish the two functions, right? So you can tell apart the Anna functions, which are the lowercase letters, and the Bruce functions, which are the uppercase letters. So we want to find formulas for the positions of the runners at time t, and then figure out who is ahead at t equals 6. So we're given velocity, so we're going to do Anna here, and we're going to do Bruce over here. So we're given the velocity for Anna, which is v of t equals 2t. So the position is going to be s of t is an antiderivative of v of t. So that'll be the antiderivative of 2t, so that'll be t squared plus c for some constant c. And remember, the way that we figure out that constant c is by using this initial value. So this s of 0 here, s of 0 equals 0, that's an initial value for the Anna initial value problem. This is going to allow us to plug in s of 0. That's going to give us, according to our formula, 0 squared plus c. But according to the information that they gave us, we know that that's supposed to equal 0. So that means that c equals 0. And so the Anna function is s of t equals t squared, plus 0, which is just t squared. Let's go to Bruce. So Bruce's velocity function, capital V of t, is just 2. So Bruce's position function, capital S of t, is going to be an antiderivative of capital V of t. That's an antiderivative of 2 dt. That'll be 2t plus c. And again, we're going to use Bruce's initial value, which is capital S of 0 equals 8. We're going to plug that in and see what we get. So capital S of 0, according to our formula, is 2 times 0 plus c. And according to the information that we were given, that's also supposed to equal 8. So that's going to tell us that c equals 8. So Bruce's position function is capital S of t equals 2t plus 8. So we've got our different position functions. That's the first part of what they asked us to do. The second part is to figure out who is ahead at t equals 6. So we're just going to plug in 6 and see which one gives us the higher position value. So s of 6, lowercase s of 6, is 6 squared. That's going to be 36. Capital S of 6, it's going to be 2 times 6 plus 8. That's only going to be 20. So it looks like Anna is ahead after t equals 6 seconds. Now, when we're doing motion in a gravitational field, so we're talking about objects falling, let's say, on the surface of the Earth, the acceleration due to gravity is a constant, right? So one of the results of the way that gravity works is that when we're standing on the surface of Earth, pretty much doesn't matter what our altitude is. This, again, if you're a physics major, you might quibble with that a little bit, but as long as we're close to the surface of the Earth, the acceleration due to gravity is always going to be 9.8 meters per second squared or 32 feet per second squared, depending on which system of units we're using. So this can allow us to solve problems with a little bit less given information. So for example, let's suppose that we throw a stone vertically into the air at time 0 with an initial velocity of 40 meters per second from the edge of a cliff that is 100 meters above a river. And we want to know with what speed does the object hit the river. So I've drawn a little picture here, but we've got our person standing on top of this 100-meter cliff. We're throwing the rock vertically up into the air. So it's going to go up for a while, but then eventually gravity is going to pull it down and it's going to land in the river 100 meters below where it started. So if we think about the information that we're given, we're told that the initial height of the rock, s of 0, is going to be 100. S of 0 is 100. After 0 seconds, the position is 100. We're also told the initial velocity of the rock is 40 meters per second. So positive 40 because the rock was thrown up into the air. Now we also know that because we're talking about motion due to gravity, that the acceleration is just constantly negative 9.8 meters per second squared. Negative here because it's pulling the rock down. So the acceleration is causing a negative acceleration for the rock, which is what's going to cause it to eventually fall. So if I know my acceleration, the velocity function is going to be the antiderivative of acceleration. That's going to be antiderivative of negative 9.8. That's just going to be negative 9.8t plus a constant. And now we're going to use the velocity initial value to figure out what that constant is. We know that v of 0 equals 40, so that means that v of 0 is negative 9.8 times 0 plus c, but it also has to equal 40, so that means that c equals 40. So that means my velocity function is negative 9.8t plus 40. Now we can figure out the position function. Position is an antiderivative of velocity. So it's an antiderivative of negative 9.8t plus 40. Again, using our antiderivative rules that we've talked about, that's going to be negative 4.9t squared plus 40t. Again, plus another constant c. I could give it another name. I could call it d. Maybe I'll do that, just so we don't confuse it with the c that we already talked about. I know that s of 0 equals 100. So that means that according to my formula, I get negative 4.9 times 0 squared plus 40 times 0 plus the mysterious d, but that's also supposed to equal 100, and that's going to tell me that d equals 100. So my position function will be negative 4.9 t squared plus 40t plus 100. Okay, so we've taken our antiderivatives, we've gotten our formulas for acceleration, our formula for velocity, and our formula for position. Now how do we answer the question? The question said, with what speed does the rock hit the water? So the velocity function is what we're going to be able to use to figure out speed. Remember that the only difference between speed and velocity is that speed can't be negative. So if we knew when the rock hit the water, if we had the time, we could plug that time into the velocity function and use that to figure out the speed. So now we need to know, when does the rock hit the water? They didn't specifically ask us that, but that's something we're going to need to know. So that means we're going to need to set the position function equal to 0. Because the river, this is position equals 0. That's height 0. So negative 4.9t squared plus 40t plus 100. I'm going to skip a little bit here. I'm going to use my quadratic formula. And that's going to give me two solutions, t equals negative 2.007 or t equals 10.17. Negative time doesn't make any sense here, so we discard that negative number, and so we say that, all right, the rock is going to hit the water after 10.17 seconds. So to figure out the speed is going to be the absolute value of the velocity at this time, v of 10.17. So that's going to be the absolute value of negative 9.8 times 10.17 plus 40. Inside those absolute value brackets, I end up getting negative 59.67. So the absolute value gets rid of that negative, so 59.67 meters per second. That's the speed that I'm looking for. So when you're given one of these motion problems, use the information that they give you to figure out formulas for velocity and position, and then you have to use those formulas to answer whatever questions they're asking.